Hello all. Today we are going to discuss about the acceleration analysis of a 4-bar mechanism. I'll read out the question and then we will discuss it in detail. The dimensions and configuration of the 4-bar mechanism shown in the figure are as follows. P1A is 300 mm, P2B is 360 mm, AB is 360 mm, P1 P2 is 600 mm. The angle A P1 P2 is 60 degree. The crank P1A has an angular velocity of 10 radians per second and an angular acceleration of 30 radians per second square. Both clockwise. Determine the angular velocities and the angular acceleration of P2B and AB and the velocity and acceleration of joint B. Now we will discuss the question in more detail. What you have is a 4-bar mechanism with link P1 P2 as the fixed link. Link AP1 is the crank, link AB is the connecting rod, and link BP2 is the driven link or the output link. You are given the angular velocity of the crank, and also it is given that the angular acceleration of the crank is 30 radians per second square. You need to find the angular velocity and angular acceleration of the connecting rod AB, angular velocity and angular acceleration of the driven link BP2. Also, you need to find the linear velocity and linear acceleration of point B, and that will be taken with respect to the fixed point P2. That is what we need to find. So this we are going to find using the graphical method, as we have done regarding the slider crank mechanism. Similar to that, we will first draw the velocity diagram and then we will draw the acceleration diagram, and from there we will find these unknown values. Now we need to start drawing the velocity diagram. To start with, since the data related to the motion of the crank is given, we will start off by drawing the velocity vector of the driving link, that is the crank. In the question, the angular velocity of the crank is given as 10 radians per second. Using that, we can find the linear velocity or the magnitude of linear velocity of point A relative to P1 using this formula, that is V equal to R omega. Here R will be the length of the crank, the radius of the radius of rotation, that is AP1, and omega is the angular velocity of the crank. By substituting the values, you can get the magnitude of velocity of A relative to P1 as 3 meter per second. So now we have the magnitude of velocity of A relative to P1. Now, regarding the direction of velocity of A relative to P1, we know that the direction will be, or the line of action of the direction will be perpendicular to the link AP1. But in the question it is given that the crank rotates in the clockwise direction. That means we can exactly find the direction of the velocity of A relative to P1, and that direction will be perpendicular to AP1 and will be in the downward direction. Okay, so this arrow indicates the direction of velocity of A relative to P1. So what you do is, from A you draw a line perpendicular to AP1 in the downward direction, and you mark the arrowhead and indicate it as velocity of A relative to P1. That means regarding velocity of A with respect to P1, we now have the magnitude, which is 3 meter per second, and also now we have the direction. Using these two parameters, we can now represent the velocity vector. I forgot to mention one thing. Before start drawing the velocity diagram, first you need to draw the space diagram, that is the diagram of the mechanism. With a given dimension, you can draw the mechanism. In this particular question, the linear units can be divided by a scale factor of 10, and you can, that is, instead of 300 millimeter, you can take that value as 3 centimeter, and you can draw the space diagram. Only the linear, as I mentioned, only the linear values has to be scaled. Now since we have now found out the magnitude and the direction of velocity of point A relative to P1, now we can start drawing the velocity vector. To draw the velocity vector, first you need to locate the fixed point. The fixed point is P1, P2. You can locate the fixed point beside the space diagram, and then from the fixed point you draw a line in the downward direction perpendicular to link AP1, that is this line, and the length of that line will be equal to the magnitude of velocity of A relative to P1, and that is 3 units. Okay, so you can take the length as 3 centimeter. You can use the scale as 1 meter per second equal to 1 centimeter. Using that scale, you can draw the velocity vector. You shall mark the endpoint of that vector as A. Also, you can indicate the velocity vector as VAP1, which indicates it is the velocity of point A relative to P1. Now we will consider the connecting rod. Regarding the connecting rod, nothing is told in the question regarding its angular velocity or the linear velocity of any point on the connecting rod. The only thing that we know is the line of action of the velocity of any point on the connecting rod with respect to any other point which is also on the connecting rod will be perpendicular to the connecting rod, that is perpendicular to AB. That means what you do is you draw a line perpendicular to link AB either from A or from B. From anywhere you can draw. Okay, so since at A you have a perpendicular line, to avoid confusion, what we will do is from B you draw a line perpendicular to AB. You can extend that line. From B you draw a line perpendicular to AB. Okay, you can extend it on either side of B. Now what you do is, from on the velocity vector, that is from point A, you draw a line parallel to this perpendicular line. Okay, so from point A you draw a line parallel to this line. Okay, that also you can extend on either side of A. This is what I have done here. Now this is the line which is perpendicular to AB, link AB, which actually indicates the line of action of velocity of B relative to A or A relative to B. In any way you can take. And I have drawn the line from the point A on the velocity vector parallel to this line. Okay. Now we will go to the next link, which is the driven link. Similar to the previous case, in the question nothing is told about the motion of, nothing is told regarding the angular velocity of the connecting the driven link. But we know that the line of action of velocity of point B relative to P2 will be perpendicular to the link BP2. So what you do is, from point B you draw a line perpendicular to BP2. You can extend it on either side of point B. Now in the velocity vector from point P2, same as P1, you draw a line parallel to this line, okay, such that the line that you had drawn will intersect the previous line, and this intersecting point will be B. Now this is the velocity diagram of the 4-bar mechanism. You can label the velocity diagram as I have labeled here. As I have told you before, what you are drawing is a relative velocity diagram. That means any vector can be indicated in any way you want, but the notation should be corresponding to the arrowhead that you are using. For example, if you indicate the arrow in this way, that indicates velocity of B relative to B, the velocity of A relative to B. If you indicate the arrow in the opposite way, then that indicates velocity of B relative to A. Now we will start doing we will start answering the question. First we are asked to find the velocity of B, and velocity of B is found relative to the fixed point P2. To find that, what do you have to do? You have to measure the line P2B, and the length of that line will give the velocity of point B relative to P2. Since we have used the scale as 1:1, the measurement that you take will be exactly equal to the velocity of B relative to P2, and you will get the velocity as approximately 2 meters per second. Now the next question is to find the angular velocity of link BP2. For that it is found out from the equation V equal to R omega. From here you can write omega equal to V by R. Now for this particular link, omega is omega of link BP2 equal to velocity of B relative to P2 divided by the length of the link, that is BP2. Velocity of B relative to point P2 is obtained by taking the length of this line, that is P2B, and then you divide by the length of that line. You get the value as 5.5 radians per second. One thing that you need to be sure, or you need to consider, is the length is given in millimeter. Here you need to convert to meters, that is you multiply it by 10 raised to minus 3. Now as the next question, we need to find the angular velocity of link AB, the connecting rod. That is also given by the same formula, that is velocity of A with respect to B divided by AB equal to omega AB. Now velocity of A relative to B can be obtained by finding the measurement of the line BA from the velocity vector and then divided by the length of that link. You get the angular velocity of link AB, which is approximately 5.83. Depending upon how accurate you have drawn the velocity vector, you will get close to these values. Okay. Now we will see how to draw the acceleration diagram for this particular 4-bar mechanism. In the question it is given that the crank rotates with an angular acceleration in the clockwise direction, and also based on the previous question that we had done, we know that for a particle which moves in a circular path, it will have two components of acceleration. One is known as the tangential component and the other will be the normal component. The normal component of acceleration will be directed towards the center, and the tangential component will be perpendicular to the normal component. Now to start drawing the acceleration diagram for this particular mechanism, first we need to calculate the tangential component of acceleration and the normal component of acceleration for a point on the crank with respect to the fixed point. First we are going to find the tangential component and normal component of acceleration of point A relative to P1. So considering the crank AP1, we are going to find the tangential component of acceleration of point A relative to P1, and that is given by the formula alpha into the length of the link. Alpha is the angular acceleration. It is given in the question as 30 radians per second. You substitute the values and you get the tangential magnitude of tangential component of acceleration of point A relative to P1 as 9 meter per second square, and the normal component of acceleration is given by the formula v square by r, where v is the velocity of point A relative to point P1 and AP1 is the length of the crank. The value of velocity you can take from the velocity diagram. In the velocity diagram, you take the measurement of line AP1, and when you substitute, you get the magnitude of normal component of acceleration of point A relative to P1 as 30 meter per second square. So now regarding the acceleration, we have obtained the magnitude of both the components, that is the tangential and the normal component. Regarding the direction of tangential and the normal component of acceleration of point A relative to P1, first we will try to understand the direction of the normal component. As we know, the normal component of acceleration will be directed towards the center point. That means here we are going to find the acceleration of the normal component of acceleration of point A relative to P1. P1 is the center point. So the direction of the normal component will be along the link AP1 and towards the center. Okay, so that means along the line of action will be along line AP1 and directed towards point P1, that is downwards. And now regarding the tangential component of acceleration, we know that the tangential component of acceleration will be perpendicular to the normal component. In that case, the line of action of the tangential component of acceleration of point A relative to P1 will be perpendicular to link AP1, and the actual direction will be along the direction of angular acceleration. In the question, the angular acceleration is given as directed in the clockwise direction. That means the tangential component of acceleration of point A relative to P1 will be directed perpendicular to link AP1 and in the downward direction. Okay, so this direction indicates the tangential component of acceleration of point A relative to P1. So now we have obtained, or now we have an idea about the magnitude as well as the direction of the tangential and the normal component of acceleration of point A relative to P1. Now using this idea, we will start drawing the acceleration vector for this particular link. To start drawing the acceleration diagram, first we need to locate the fixed point. Fixed point here is P1, P2. In the acceleration diagram, all the points are labeled using small letter alphabets with prime. So first you locate the fixed point, and then after locating the fixed point, it will be better that we first indicate or represent the normal component of acceleration. To draw the normal component of acceleration, you have to draw a line from the fixed point parallel to the link AP1 in the downward direction. That is what I have done here. First, you locate the fixed point P1 prime, P2 prime is the fixed point, and from the fixed point you draw a line parallel to line AP1 or the link AP1 in the downward direction. Okay, the length of the line will be the magnitude of the normal component of acceleration of point A relative to P1, and that is 30 meter per second square. So 30 meter per second square will not be possible to be represented. So what you can do is you can divide that using a scale factor of 5. In that case, the length of this line will be 6 centimeter. Okay, the end point of this line can be indicated by the alphabet X. Okay, also please note that since we are indicating we are drawing the component of acceleration, the component of acceleration should be represented by dotted lines. You can indicate the normal component of acceleration as I have indicated in the figure using the arrowhead, and you can denote it as the normal component of acceleration of point A relative to P1. Now we need to indicate or draw the tangential component. The tangential component of acceleration will be normal to or perpendicular to the normal component, and also we know the magnitude as well as the direction. So what you do is, from point X you draw a line perpendicular to the normal component in the downward direction. Okay, I hope you understood why we are taking the downward direction, because that is the direction of rotation, and the length of this line will be the magnitude of the tangential component of acceleration of point A relative to P1, which is nothing but 9 meter per second square. This value also you need to divide by the scale factor of 5. Now onwards, every acceleration component will be divided by the scale factor of 5. So that will be coming around 1 point something, 1.8 something. So with that value you draw the tangential component, and the end point of that line will be A prime. and also you label as I have done it here. You label using the arrow mark, and then note it as the tangential component of acceleration of point A relative to P1. So now you have got A prime. Now what you can do is you can join A prime with P1 prime, P2 prime. Okay, so this line represents the absolute component of acceleration or absolute acceleration of point A relative to P1. Okay, next we can either consider the connecting rod AB or the output link or the driven link BP2. Here I am going to consider first the connecting rod AB. Regarding connecting rod AB, like in the previous question, here also there is a slight confusion whether we need to consider that point A is rotating about B or whether B is rotating about A. Then in the case of the acceleration diagram, if A is rotating about B, we will write A acceleration of A relative to B. And if you are considering B is rotating about A, then we will represent it as acceleration of B relative to A. In the acceleration diagram, acceleration of A relative to B is noted as B prime A prime, and acceleration of B relative to A is denoted as A prime B prime. We will take that particular option whose starting point is known. In that case, since A prime is known to you now, we can take this particular option. That is, we will assume that B is rotating relative to A. Okay. So now in the acceleration diagram, we are going to represent acceleration of B relative to A. Acceleration of point B relative to A will have two components like usual. One is the tangential component and the other is the normal component. First we will try to find the magnitude of the tangential component and the magnitude of the normal component. The magnitude of tangential component of acceleration of B relative to A is obtained by the formula alpha into R, where R is the length of the link AB or BA and alpha is the angular acceleration of the link BA. But in the question, the angular acceleration is not given. That means at this particular point, we will not be able to find what is the magnitude of the tangential component of acceleration of B relative to A. So we will leave that right now. We will move on to the normal component of acceleration. Regarding the normal component of acceleration of B relative to A, that is given by the formula V square by R, where V is the velocity of B relative to A that can be obtained from the velocity diagram. We can measure the length of the line BA in the velocity diagram. That will give you velocity of B relative to A, and you divide that with the length of the link BA, and you will get the distance, we will get the acceleration magnitude, the magnitude of normal component of acceleration of B relative to A as 12.25. Now to represent it in the acceleration diagram, we need to divide this with the scale factor of 5. Okay. So now we have got the magnitude of the normal component of acceleration of B relative to A, and we know that regarding the direction of normal component, the direction of normal component will be towards the center of rotation. Here the center point is A, so the direction will be along the link BA towards point A, that is in the downward direction. Okay, so what you do is, in the acceleration diagram, from point A prime, you draw a line parallel to link BA downwards. Okay, and the length of this line will be the magnitude of the normal component of acceleration for B relative to A. You can take the end point of that line as y. Also, since we are representing the component, we have to draw using dotted line, like I have done here. And after denoting the end point y here, you also have to mark the arrowhead and denote the acceleration component. After representing the normal component, regarding tangential component, we know that the tangential component of acceleration of B relative to A will be perpendicular to the normal component. So what you do is, from point y, you draw a line perpendicular to the normal component. Okay, that also should be drawn using dotted line. You can extend this line on either side of y. Now we need to consider the driven link or the output link BP2. In this particular link, since point P2 is fixed, we need to consider the acceleration of point B relative to P2. So similar to the previous cases, to find the acceleration of point B relative to P2, first we need to find the magnitude of the tangential component and the normal component of acceleration. Regarding the tangential component of acceleration of B relative to P2, it is given by the formula alpha into r, where r is the length of the link and alpha is the angular acceleration. Here also the angular acceleration of link BP2 is not known or not given in the question. So that means we cannot proceed right now regarding the tangential component. So we will find out now the normal component of acceleration of B relative to P2, and that is given by the formula v square by r. V is the velocity or the relative velocity of B relative to P2, and that can be obtained from the velocity diagram. You measure the length of the line BP2 in the velocity diagram, and BP2 is the length of the link BP2. You get the normal component of acceleration as 11.11 approximately, and this to be introduced in the acceleration diagram, we need to divide it by the scale factor of 5. We have now found out the magnitude of the normal component of acceleration of B relative to P2. The direction of the normal component of acceleration of B relative to P2 will be towards the center. That means the direction will be along the line BP2 or parallel to the line BP2 towards point P2, that is in the downward direction. in the acceleration diagram, from point P2 prime you draw a line parallel to the link BP2. From P2 prime you draw a line parallel to the link BP2 in the downward direction. The length of this line, that is P2 prime Z, will be the magnitude of the normal component of acceleration of B relative to P2. And then once you draw the normal component of acceleration of B relative to P2, from Z you draw a line perpendicular to the normal component, such that that perpendicular line will meet the previous perpendicular line at B prime. Since these two lines, these two lines are components, that has to be drawn with discontinuous lines like usual. Okay. So now we have now got B prime. Now we need to join all points, that is B prime to P1 prime, P2 prime, and B prime to A prime. And already P1 prime, P2 prime is joined with A prime. So now what you get is the acceleration diagram. So you can see here, this is what you will get finally. And you need to label all points and also indicate all accelerations as I have done it. Like this point, this line indicates acceleration of A relative to P1. I have indicated the arrow mark like this. And this line indicates that is A1 A prime B prime indicates acceleration of B relative to A, and line P1 prime P2 prime B prime, this line indicates acceleration of B relative to P2, point P2. So all these notations has to be copied. Okay, so this is the acceleration diagram for the 4-bar mechanism. Since we have completed the acceleration diagram for the 4-bar mechanism, now using this acceleration diagram we will find out the unknowns that are asked. The first question that is asked is the acceleration of point B, which will be relative to the fixed point P2. To find the acceleration of B relative to P2, you need to measure the line B prime P1 prime P2 prime. Okay, so this line will, the length of that line will give the magnitude of the acceleration of B relative to P2. That will come approximately 29.5 meter per second square. You can check your answer. Depending upon the accuracy with which you have drawn, the value can slightly change. Now the next question is to find the angular acceleration of link BP2. The angular acceleration is related to the tangential component. Now the equation for tangential component of, or the magnitude of tangential component of acceleration of point B relative to P2 is given by alpha into R. So from this equation, R is nothing but the length of the link BP2. From this equation you can get the angular acceleration as the magnitude of tangential component of acceleration of B relative to P2 divided by the length of the link. So this will come around 76.39. Also the tangential component of acceleration of B relative to P2 can be obtained from the acceleration diagram. Tangential component of acceleration of B relative to P2 will be the length of the line Z B prime. Okay, so that is the tangential component of acceleration of B relative to P2. So when you substitute that in the equation, in this particular equation, you will get the angular acceleration that will be 76.39 approximately. Unit is radians per second square. Next is to find the angular acceleration of link AB. That is also obtained from the same formula. In that, the formula is for the the magnitude of the tangential component of acceleration of B relative to A, that is equal to the angular acceleration of BA, link BA, into the length of the link BA. From this equation, you can get the angular acceleration of BA, link BA, that is equal to the tangential component of acceleration of B relative to A divided by the length of the link BA. And here also the tangential component of acceleration of B relative to A can be obtained from the acceleration diagram, and that is obtained the tangential component of acceleration of B relative to A is obtained by the length of the line Y B1 B prime. So this line, the length of this line will give the tangential component of acceleration of B relative to A. You substitute that and divide by the length of the link, you get the value for the angular acceleration as 43.75 radians per second square. So this is what it is.